Hi, welcome to Geometry Chapter 2, 2.5 Reasoning in Algebra and Geometry. Our objective is to connect reasoning in algebra and geometry. The essential understanding that you'll develop through this lesson is that algebraic properties of equality are used in geometry. They will help you solve problems and justify each step you take. In geometry, you can accept postulates and properties as true. Some of the properties that you accept as true are the properties of equality first introduced in algebra. A key concept here are the properties of equality. Let's let A, B, and C be any real numbers. We're going to talk about this in symbols and in example. Each of these properties, several of them are properties that you are already familiar with. For example, the addition property. If A is equal to B, then A plus C is equal to B plus C. You can add the same thing to both sides of any equation. An example would be this. If x is equal to 2, then x plus 2 is equal to 4. We added 2 to both sides of this equation. Subtraction property. That's when you subtract the same number from both sides of an equation. So if A is equal to B, then A minus C is equal to B minus C. An example of this would be, if y is equal to 8, then y minus 3 is equal to 5. We subtracted 3 from both sides of the equation. Multiplication property is when you multiply both sides of an equation by the same term. If A is equal to B, then A times C is equal to B times C. An example of this would be, if Z is equal to 2, then 5 times Z is equal to 10. We multiplied both sides of this equation by 5. The division property we frequently use when you divide both sides of an equation by the same term. If A is equal to B and C does not equal 0, then A divided by C would be equal to B divided by C. An example of this would be, if 6 times m is equal to 12, then m is equal to 2. We divided both sides of this equation by 6. Now we have the substitution property. Substitution, if A is equal to B and A can be substituted for B in any equation or expression. An example would be this. If 3x plus 5 is equal to 3 and x equals 2, then you could take out the letter x and put in the number 2 in its place. Next we have the distributive property. If any term is outside of a parentheses, then that means that term is passed out or distributed to anything within the parentheses. A times B plus C would be equal to A times B and A times C. An example of this would be 3 times x plus 4. It's equal to 3 times x and 3 times 4, which is 12. These are the properties that we've already used and explored last year in algebra and the beginning of this year in Algebra 2 and Geometry. This year you were also introduced to these 3 new properties: reflexive property, symmetric property, and transitive property. These are also properties of equality that we have explored. The symbols for reflexive property: for any real number A is equal to itself. That's when one thing is equal to itself. An example would be AB is equal to AB for any segment, the distance of AB. Symmetric property. If A is equal to B and B is equal to A, so that's 2 things, A and B. It's forward and backwards. If xy is equal to ZA, then ZA is equal to xy. Transitive property, that's when we're talking about 3 things. So reflexive was 1 thing to itself. Symmetric was 2 things, forward and backwards. Transitive is 3 different things. If A is equal to B and B is equal to C, then A is equal to C. If KL is equal to MN and MN is equal to TR, then KL is equal to TR. So the first thing equals the second, the second is equal to the third, then the first is equal to the third. 1 to 2, 2 to 3, then 1 to 3. And this could be 3 or more. This could go on like the domino effect. We've discussed that in class. You use deductive reasoning when you solve an equation. You can justify each step with a postulate, a property, or a definition. Using our laws of logic is using deductive reasoning. Example 1, justifying steps when solving an equation. What is the value of x? We're going to justify each step. We're given here that ray AB bisects angle RAN. So ray AB bisects angle RAN. Therefore, we know the measure of angle RAB is equal to the measure of angle NAB by the definition of bisects. So this is the reason we can give. The measure of angle RAB is equal to the measure of angle NAB using the definition of bisect. That word tells us that it cuts this angle into two congruent angles. Using substitution, we know that angle RAB is equal to x, so we'll put it in its place. We know that angle NAB is equal to 2x minus 75, so we'll put it in its place. This is using substitution. That's our justification for this step. Our next step would be to subtract 2x from both sides of this equation. We would get negative 1x is equal to negative 75 because we use subtraction property of equality. And lastly, to find what the value of x is, we would divide both sides by negative 1 to solve that x is equal to 75. We use the division property. Because we knew that ray AB bisects angle RAN, and the definition of bisects meant that these were equal to each other, then we could find out that x would equal 75 using our properties of equality. Some properties of equality have corresponding properties of congruence. You'll know that they're properties of congruence because instead of an equal sign, they have a congruent symbol. The property set we have are reflexive property, symmetric property, and transitive property. Reflexive property of congruent is when a segment is congruent to itself. Segment AB is congruent to segment AB. It's one thing congruent to itself. It can be said of angles also. Angle Z is congruent to angle Z. This is true of every segment and every angle. They are congruent to themselves. Symmetric property. Again, that's when there are two geometric figures. If segment AB is congruent to segment CD, then segment CD is congruent to segment AB. This is also true of angles. If angle Q is congruent to angle R, then angle R is congruent to angle Q. Lastly, we have the transitive property. Remember, this is when three or more things. So, if segment AB is congruent to segment CD, and segment CD is congruent to segment EF, then segment AB is congruent to segment EF. This is also true of angles. If angle 1 is congruent to angle 2, and angle 2 is congruent to angle 3, then angle 1 is congruent to angle 3. Reflexive is one thing that's congruent to itself. Symmetric, two geometric figures that are congruent to each other. And transitive, three or more. Three or more. And it's like the domino effect. The first thing would be congruent to the last thing in that line. Example 2, using properties of equality and congruence. Complete each statement and determine which property is being used. If angle P is congruent to angle R and angle R is congruent to angle A, then angle P is congruent to angle A. This is using the transitive property. The first is congruent to the third. This is transitive property of congruence, and you know this because there's a congruent symbol there. Let's look at the second one. If angle X is congruent to angle N and angle blank is congruent to angle Y, then angle X is congruent to angle Y. Well, X is the first thing and Y is the third. What needs to go in here in this space? That would be angle N. And again, this is using the transitive property of congruence. Look at the last one. If angle L is congruent to T and angle T is congruent to angle blank, then angle L is congruent to angle Q. What angle would angle T have to be congruent to in order for angle L to be congruent to angle Q? That's right, angle Q. And again, this is an example of the transitive property of congruence. A proof is a convincing argument that uses deductive reasoning. A proof logically shows why a conjecture is true. A two-column proof lists each statement on the left and the justification or the reason for each statement on the right. Each statement must follow logically from the steps before it. Example 3, writing a two-column proof. Here we're given that segment AB is congruent to segment CD. AB is congruent to CD. We want to prove that AC is congruent to segment BD. Do you think that you can? How would we get there logically? That's what a proof is. So let's write our first proof together. Step 1, we would say that AB is congruent to CD. Why would we say that? Well, where did that come from? That was given to us. So our reason for this would be given. Step 2, if we know these two segments are congruent, then we can say we know they are equal. If segment AB is congruent to segment CD, then the next logical step for me to say is that I know that they are equal. And this is the definition of congruence. Step 3. What do I know now? Well, I know that segment BC would be congruent to itself. Every segment is congruent to itself using the reflexive property of equality. Then I know if I put two segments together, if I add BC to both sides of this equation, if AB was equal to CD and BC is equal to itself, then I can add BC to both sides of this equation in step 2. This is using the addition property of equality. So you see what we did there? In step 2, we had that AB was equal to CD. Step 3, we said BC was equal to itself. So step 4, we added BC to both sides of this equation using the addition property of equality. The next step, when you put two segments together to get a bigger segment. AC is equal to BD. When you put two segments together to get a bigger segment, AB plus BC is equal to AC, and BC plus CD is equal to BD. We use the segment addition postulate. Postulates, definitions are all, and properties are all accepted for reasons in proofs. Therefore, if AC is equal to BD, then we can now prove what we set out to prove. AC is congruent to BD. If they were equal, why are they congruent? Because that's what the word congruent means, the definition of congruence. So again, let's take a look at our proof. Step 1 we knew because it was given to us. AB was congruent to CD. We knew if they were congruent, then that they were equal, because that's the definition of congruence. Then we said BC is equal to itself. That's the reflexive property of equality. In step 2, we said AB was equal to CD. In step 3, we said BC was equal to itself. So in step 4, we know that if we added the same thing to both sides of an equation using the addition property. Step 4 went to step 5 because when you add two smaller segments together and get a bigger segment, you're using the segment addition postulate. And finally, from step 5 to step 6, we knew that if these segments were equal, then they were congruent, because that's what the word congruent means. Proofs take a little bit of time. This was our first one together. We'll practice this more in class. Let's try another one. Example 4, writing a 2-column proof. This time we're going to use some angles. So let's look at our given information. We're given that the measure of angle AQB, so that's this one here, is congruent to the measure of angle is equal to the measure of angle CQD. You know if they're equal, then they're congruent. We want to show that AQC is equal to the measure of angle BQD. So it's along the same lines as the proof we just did, because we want to use this angle here in the center, angle BQC. So step 1, the measure of angle AQB is equal to the measure of angle CQD. Usually in step 1, you always put this bit of information. We got that because it was given to us. The next step that we're going to take is that we know that AQC, that's this one, is equal to angle AQB plus angle BQC. When you add two angles together to get a bigger angle, well, that's using the angle addition postulate. We added AQB and BQC to get this larger angle, AQC. We added two angles to get a bigger angle. Our next step is going to be angle AQC is equal to the measure of CQD and BQC. What? How did we do that? Well, in step 1 we said AQB and CQD were equal. Then in step 2 we said AQB plus BQC is this bigger angle, AQC. What did we do with step 2 and step 1 to get to step 3? We took out AQB and put CQD in its place. We used the substitution property of equality here. In step 2, we had AQB plus BQC equals AQC. From 2 to 3, we took that out and put CQD in its place because in step 1, we said they were equal. Step 4, how did we get from here to here? What changed? We added these two angles together to get this bigger angle. Measure of angle BQD is equal to CQD plus BQC. We're using the angle addition postulate to add two smaller angles together to get a bigger angle. Then finally, our next step. If we knew that AQC was equal to QCD and BOC, and we knew that BQD was equal to CQD and BQC, then we can say they're equal to each other. How did we do this? We used substitution. We took this out and put this in its place. Substitution. There was more than one way to do this proof. This was the route that I chose to do it. Just like when you leave my room and walk to the cafeteria, you could go one way and I could go another, but we could still get to the same place. I took a different route than maybe you saw at the beginning, but we're going to talk about this in class tomorrow. That's the end of our lesson today. That's the end of these notes. Tomorrow in class, we're going to apply these. It's very important that you take the notes. If there's something that you don't understand, please rewind this video and go back to it. Pause the video along the way to take notes. If you have questions, please write them down in your notes, and tomorrow in class, we'll address all of your questions. Have a good night. See you tomorrow.